All right, can y'all hear me okay? Okay, cool. I wanted to go over a couple of things and then finish lecturing on the material in this chapter. So I just have comments regarding the video you turned in. Basically, I was just looking for. I was really just looking for whether you built a device and it worked somehow. Not everybody, in regards to electrophorus, not everybody used charging by induction to demonstrate the electrophorus. The electrophorus is a device that's used to illustrate charging by induction. So for the lab, you have to demonstrate charging by induction. Okay, so let me show you that. Let me get a quick drink of water and I'll show you that. So here's the electrophorus. I mean, I really don't have a surface to do this on, and then some of you folks, clever enough to use styrofoam as the object you charge. Because I said in the lab, use saran wrap or acetate. You can use this too. This works fine. Okay. So some of you guys charged up a piece of a paper plate, probably bigger than this. All right, that is what I have right now. And you rubbed it with fur. I know the fur was bad. Okay, we'll talk about that. Or wool. You charged it up. Because some of you took the electrophorus and brought it near the surface of the charged object. You touched the plate to ground and demonstrated that this was charged. Some of you, and that is charging by induction, by the way. Some of you put it directly on top. This is what I asked. And you touch the hand to ground. The reason why I asked you to have one hand, the other hand touching an appliance that's grounded, it just makes it easier for the electrons to come and go to the ground. Because if you don't do that, you just got to make sure that you're not standing on something that's very well insulated. You don't want to have rubber shoes on or anything like that. Okay. But the best way to do it is put one finger here, the other hand goes to a grounded appliance, and this will get charged up. And then what you can do is hover this over some pieces of paper that are charged. Now, what a bunch of you guys did, and this is not charging by induction, okay? You rub either the saran wrap or the acetate or the styrofoam plate. You charged it up. You put the plate on top, and then what you did, you just touched it and listened to a spark. That's not charging by induction. You haven't proved to me that you charge it by induction. Okay? In order for you to prove to me that you've charged it by induction, you have to be able to lift this up, and you have two options. One, you can bring your finger near it and hear for a tick. Of course, the person watching the video has a hard time hearing that. But then the other, you can actually move it over some aluminum foil or some paper, and if the paper moves or the aluminum foil moves, then you show that this thing is charged. So you have to be able to do that in the lab, because otherwise you'll lose points. Because that's really where I'm testing you. Do you understand what charging by induction is? And can you do it? Now, building these apparatus, like this is easy to build. Building the electroscope, obviously was easy to build. And there's a lot of things in engineering that are like that. They're pretty easy to build, but making it to work is another thing. Finding out what's going wrong and fixing it is part of engineering. It's part of science. Troubleshooting is part of both of these fields. And so what you have to do is learn how to troubleshoot. So some folks prefer and the ceramic didn't work. What do? They got a styrofoam plate. Okay, and it's fine. You just have to demonstrate electrophorus. It doesn't have to be exactly the same material as what's in the link that I sent you. Because I said a couple of weeks ago, that's just one of the designs. You can use other designs. It just has to be electrophorus. So there's going to be another lab later on the semester where you're going to build an electromotor, and it's going to have to work under certain conditions for you to get a certain grade. And it's easy to build, but you got to build it right if you want it to work easily. So it's got to take great care and troubleshooting on your part to be able to make it work right. That's part of engineering. That's part of science. But those are skills you have to learn in the real world. And that's what we're trying to teach you. Okay, so just be aware of that. So if something doesn't work, that happens to everybody. Okay. They build something, they put it together the first time, and it doesn't work. Then your job is to figure out what's wrong, and your job is to make it work. Because when you're on the job as an engineer, that's what you're getting paid for. Okay, you're getting paid to make something work. And so, you just have to think a little bit about why, how the device works, and what you need to do to make it work. You can get it to work. Okay. So most people did a good job. The electroscope, most people got it to work. Actually, I think everybody got it to work. In fact, one person didn't use a jar; they used a drinking glass. That's fine. We can use a drinking glass. Okay, they thought out of the box. So okay, I'll make my electroscope out of a drinking glass. Of course, you need a bigger drinking glass, right, to be able to do it. But they did it. One of the issues with getting the electrophorus to work right is that the aluminum foil can't be crinkled. It's got to be as straight as possible. But I saw some of them, the foil, the leaves of the electroscope, they wouldn't open up very much. And then when you look at the leaves, they're kind of crinkled. And make sure they're not heavy either. Because if they're heavy, and the other thing too, you can separate the two pieces. Some people just take a long piece of paper and put it over the support. And what happens is the whole thing spins. You don't want that. You just want the leaves to move independent of each other. Okay, you want the leaves to move independently. So you can actually cut the leaves, make them separate, and attach them to the support so that they can move independently. You might want to think of making the leaves out of longer narrow strips instead of wide strips. Wide strips will will make it harder for the leaves to move. These are engineering things you got to think about. Okay, if you want to make something work more easily. Okay. Because when you take the engineering courses, you're going to be expected to do those. When you take, for example, patent bills courses, you're going to be expected to make those kind of considerations when you're designing something. What can I do to make it work right? Okay. But most of all, most people did a good job. There were a couple of people who I wasn't understanding how they were trying to charge the profits, but most people did fine. So the next part then is you have these working devices. Now you're going to go through some of the exercises in the lab, and you're going to explain them. Observe. You're going to make a video showing some of these effects, and then you're going to explain them. So if you have several phenomena that can be explained using the same idea, you don't have to show every single one. You can show one of them and say that the other ones in the lab work using the same idea. Okay? You can just pick one of them, demonstrate it, and say, oh, these other things work by the same idea. You want to use the ideas that we talked about in class, the words that we talked about in class, to explain why things are happening. I want you to be able to integrate the stuff we talked about in class to what you're experiencing in the lab.
So is this the next assignment? Is to the explanation of it?
Yeah, so you're going to go through that whole exercise, right? There's 3 steps to it. There's 3 parts to it. You're going to rub the balloon on your head, see if it sticks to the wall, that kind of thing. You're going to take the PVC, bring it by the water, and see if it bends. Okay. You're going to go through that, and you're going to explain what's going on. Is that clear? Or
Did you want us to explain it in writing or in like a video?
no, video. It's a video, right? It's a video report.
Okay.
Yeah,
right on.
I don't want. Yeah, I want this to be a video report. It actually, I think it's hard for the students in general to write this up, and I'm hoping that having you make the video, one, it'll make it easier for you, and 2, it'll give you a better understanding because you have to verbalize concepts, which is a big difference than writing things down. Now, some of the videos that some of you folks sent were very long, and I'm so happy that you put them on YouTube. It's video, you are encouraged to take a video and put it on YouTube, especially if it's long. And I never visioned this. Some of you used there's a video capture software within Canvas. They use that to create the video. So all I had to do is click the button and I watched the video. And I didn't envision that when I created this assignment. So I'm going to go through and play around with that so I can show, maybe have everybody use that or actually just upload videos onto YouTube. And some of you just created a video, they uploaded it. The only problem I had was when I had to download every single video because it wouldn't play in Canvas. Those of you who uploaded a video made it, on with your camera or whatever. I had to download them, and downloading stuff from Canvas takes forever. And I had to view them, so that process was slow. But a couple of you either used YouTube, which was great, or you used the Canvas Studio to create the video. So I just said, those of you in the Canvas Studio, I just clicked the button and it worked. That was so nice. So I'm going to go through and play around with it and see how we can make that easy for us. Because if you're going to make a 6-minute video, for example, and you're going to upload it, and then I have to download it, both of us are spending a lot of time with that. But if you can send it to YouTube, if you do it to YouTube, you just upload it to YouTube, give me the link, and everything's done. Okay. YouTube makes things pretty easy for us. Do you have any questions regarding this report? Because this is going to be due on the 18th.
Okay, I was just about to ask that. Okay, sounds good.
Okay. Yeah, it should say in your calendar on Canvas, it'll be due on the 18th. So, again, get started early. And just, again, it doesn't, because I had people asking me the other section, do you want us to edit it or whatever. It doesn't have to be edited. You can start the video, demonstrate something, stop it, and then start it again for the next thing. You don't have to, you can do it however you want, and you don't have to spend time editing unless you like doing that. It's up to you. Okay. I don't want it to be a burdensome thing. I don't want the video process to be overly burdensome. If you have a PC, if you have a computer or a laptop with a camera on it, it's actually the best thing because then you can set the camera down, the computer down, and then you can actually videotape yourself doing things. With a camera, it's a little bit harder, unless you have a stand for it. So any questions? Concerns? For the most part, I thought it was cool what you guys did, so I was happy. You're never sure Oh yeah, so this was something new because we're online. Everything we're doing is new. I need to know, because I'm going to try to do these labs again next semester, about the equipment. I know one piece of equipment that didn't work very well. It was the fur. It sheds like crazy.
Yeah, I have that everywhere in my room.
Yeah, and so this was a couple of days, or maybe one day before we had to hand out the lab kits. We had to cut the fur. And then I picked up the fur and carried it, all of it at once. My entire shirt was full of fur. So I started becoming concerned with that. We're trying to use synthetic fur, right? Not real fur. So that could be, and it was very inexpensive. We're trying to keep the cost down. But on one hand, you're trying to keep the cost down, but on the other hand, you want to make sure that you can do the experiment. So we need to know if a piece of equipment is not good. I know that one is not. However, the wool can work for charging objects. So if the fur is problematic, which, especially if you're using fur with PVC, it should work. If it doesn't, then you use wool, a piece of wool that we sent you. Okay. But please email us regarding this lab, because I want to know how it works. Because the original lab, when you do it on ground, there's 5 parts to it. But the other 2 parts, one involves the fun part, the Van de Graaff. You get to shock yourself with it. We can't do that. And then the other one is the Kelvin generator, which I wouldn't even have you build it because that would take time. Okay, so we missed out on that. But we try to do whatever we can with what we have. So let us know during a semester how the equipment works. And we need to know. We need your input. Okay. If a lab was too hard to do, tell me what happened and why as we go through the semester. That way we need to know early, because we have to order the equipment for, most likely next semester will be online. It's not official, but everything's pointing to that. Okay. So we need your feedback. It's important. Okay? All right, so in the meantime, then I'm going to finish off the discussion I've had regarding Gauss's law. Applications. So I'm going to do a couple more examples, and then I'm going to talk about conductors and electrostatic equilibrium. And then I forgot about it. I have another example after that. So I'll cover all that in this time. All right. So the first example where we applying Gauss's law is we want to calculate the electric field due to a rod. It's a thin rod that has no thickness. And while you look at that, I want to erase the board. It has a uniform charge density lambda. And in order for us to be able to use Gauss's law, a rod has to be infinitely long. Because what happens at the ends, the electric field bends in a shape that makes it hard for us to pull the E dot N out of the integral. And I'll show you why. All right, now I have my board erased. So let me draw a line charge. In fact, let me draw a short one and a longer one. And here's my long one. Lambda. Let's pretend it's infinitely long. I can't draw something. It takes me too long. Too much time to draw something infinitely long. Here's a short one. And if you draw the fields due to it, let's say it's positively charged, the field lines will probably look like this. At the ends, it really bends. If you make this longer, these actually straighten out. Remember the idea, remember the 2 positive charges? We did the electric field into the positive charges, the field lines did this. The more you place along the line, the straighter these guys get. And so these field lines will straighten out as you make this long. If you make it infinitely long, these get perfectly vertical. Then you can use Gauss's law. And we're going to do the same thing when we do the infinite plane. Okay, so here's my rod. It's a one-dimensional object. And we want to calculate the electric field due to the rod. So my Gaussian surface has to have the same symmetry as the rod. Well, I'm not going to choose a sphere because a sphere and a rod don't have the same symmetry. But a cylinder does. A cylindrical shell has the same symmetry. So I'm going to draw it in green. I usually don't use green. It's hard to see, but here's our cylindrical shell. Again, as a reminder, this is an imaginary surface that is going to allow us to analyze the system. It's not a real surface. It's just something that's going to help us to analyze the system. And you're going to learn more about this kind of thing in Top 3. And the radius of this thing is R. So the electric field, due to the rod, is just going to be pointing upward, like so, or downward on the other side. If you think in 3 dimensions, you'll have lines also coming down towards us, and then lines also going into the void. If you think 3-dimensionally. The normal to the surfaces, the normal to this surface is obviously going to point straight down below, straight up above. So if you want to use this equation, you should realize that for any value of R, the electric field is going to be the same, and it's going to be parallel to the normal to the surface, all the way along the lateral surface of the cylinder, the round part of the cylinder. Now the cylinder has 3 surfaces. It has this part and then the ends. But there's no field lines that penetrate the ends of the cylinder. There's no red arrows that penetrate the ends of the cylinder. So we don't even have to worry about those ends. You have to worry about this end, that's at positive infinity, and the one that's at negative infinity. You have to worry about it because the red lines don't penetrate those surfaces, because the red lines point radially, and these planes point perpendicular to the red lines. So the dot product is always 0. The only one we have to consider is the lateral surface. Okay. And so the name of the game now is to do the integral over the lateral surface. Since this is constant over along the entire surface, and E is parallel to N all the way around, then I can just pull the E out of the integral. Now my dA is the surface area of that yellow cylinder that you see, the lateral surface area. So that's going to be equal to E times 2 pi, right? It's going to be the circumference times the length. And you're going to say, wait a minute, L is infinite. That doesn't make sense. Yes, you are right. Let's just leave the letter L there for now. Okay, we'll leave the letter L and we'll see what happens. Okay? I know this looks weird because this is infinite. But watch what happens in a minute. How much charge is enclosed inside the green surface? Well, it's just going to be
0?
well, no, you have the rod inside, right? Isn't it true that the rod inside? And if the rod, so it's going to be lambda times the length of the rod. And you say, wait a minute, that's also infinite. I know it's weird. Guess what happens to the L's? Is the L here on one side of the equation and the L here up at the top on the other side? And so I have so E is lambda over 2 pi r epsilon naught. And remember, using that relationship between epsilon and Newton's constant, I'm sorry, Coulomb's constant, could be written that way. That's it. That's the field due to an infinitely long rod. Now you might say, why do a problem like this? Because it's not real. Where are you going to find an infinitely long rod? Right? I mean, isn't it kind of weird to think of anything in one rod? Let me pose you this question. Suppose you had a rod that was not infinitely long, and you wanted to calculate the field real close to it. Almost on top of it. And in fact, if you were sitting on top of that point, the rod would look very, very long. If you actually did the calculation like we did in the previous chapter, you would, and then you use an approximation for big L, you would get an equation that looks just like this. So this is an approximation for the case where you have a finite sized rod and you're determining the field real close to it. In other words, you want, if R is much, much less than L, then you should be able to use this equation as a good approximation for the electric field. Does that make sense? Now in physics, in the real world, a lot of problems are hard to solve mathematically. And so physicists love to do, they call them back of the envelope calculations. And so if they can do an approximation to a problem and get a result, they can actually understand the system. This is the case where you can do an approximation. If you're real close to the rod, you use Gauss's law because it looks infinitely big. And one of the things you learn in physics is to understand when you can use the correct approximation to understand the system. That's a hard thing, but that's something that's important to learn. Actually, not only as a physicist, but also as an engineer. You're probably a chemist too. Okay, so what if, hold on a second. Oops. Okay, what if we replace the rod with a cylinder? In other words, what if instead of a rod I had a thick rod? All right, this is a one-dimensional thing. What if I had a thick rod? Then what? Well, then I can find the electric field if this is charged, and however this is charged, I can actually use Gauss's law to find the field inside it. As long as the charge distribution is nice, I can find the field inside it, and I can find the field outside it. Finding the field outside it is doing this. Finding the field inside is exactly the same as the sphere problem we did at the end of class. The only thing is, instead of a sphere, you have a cylinder. Same process, geometry is different. Okay. Same idea, just the geometry is different. That's it. But one of the things in doing these problems, you got to be able to see the big picture, right? Because whether I do a cylinder or a sphere, it's the same process, just the geometry is different. The same physics, just the geometry is different. Let's do another example. I created a video, I think it was last week, where I calculated the field due to a disk by elementary principles, the principles of chapter 22. And I also did, I looked at the case where we calculated the field real close to the disk. So I did a problem with the disk. And I said, what if it's real close to the surface of the disk? What's the electric field look like? And I showed in the video that the electric field looks like this. Real close. It's approximately that value. Of course, if you're real close to the disk, if you're real close to the surface of a disk, the disk is going to look infinitely big. So now what I'm going to do is a plane, because an infinitely big disk is a plane. And so I'm going to calculate the electric field due to an infinite plane and see what we get. All right, let me draw my plane. Okay, I gave it with some thickness, but imagine it's infinitesimally thin. Okay. Let's pretend it's positively charged. The charge density is sigma. And so I'm going to show you what the field lines look like. It's kind of like a rod, except that the field lines are scattered in two dimensions. I have to draw these arrows really in two dimensions, even though they're. You can imagine these field lines coming out, the plane coming out this way, then I have a bunch of arrows going in that direction. Okay, so those are my field lines. Intuitively, we know that. So, what kind of Gaussian surface am I going to use to be able to extract the electric field from the system? To determine it, right? I want to be able to choose a Gaussian surface so I can pull the E dot n out of the integral, so I can calculate the integral very easily. I'm sorry, so I can calculate the electric field very easily. I'm going to use a cylinder again. So my cylinder is going to look like this. It's going to be a short cylinder. In the previous example, it was a long cylinder. This is a short cylinder. I didn't draw that very well. I'm not an artist. Anyway, I'll just leave it at that. That's not a good picture, but I think you understand what I'm trying to do. Okay. Notice that the field lines do not penetrate the lateral surface of that Gaussian surface. The field lines only penetrate the ends. The field lines only penetrate the ends. They don't come out towards us. And so when I calculate the flux over the entire surface, I'm only considering this end and this end. By the way, this is a cylinder. When I was a student, they call this a pillbox. And there's very few authors that use that term now. Pillbox refers to a short cylinder, that's all. Okay. That's all it means, short cylinder. So the field lines penetrate just these sides. So I'm going to write the normal to the surfaces. The dot product at E dot N is going to be the same all around this round part here. If you want to call the surface area of this thing, I'm sorry, the area of the circle pi r squared, go for it. I'm going to call it A. Okay. Now, when I drew my picture, be careful. I mean, I drew it like this. I didn't want to draw it. It really should enclose the entire charge distribution. I didn't do that. That's something that we usually do in physics book, because if you draw it so it encompasses the radius, so it encompasses the whole charge distribution, the picture gets ugly, I guess. So we don't do that. But just assume that this cross-sectional area is the same as the area of the plane, which is infinite. Okay. So, same thing again. I'm going to use this expression, but I can pull the E dot N. And since E and N are parallel, the dot product gives you E. So on this side, E dot N gives you the magnitude of the vector. On this side, E dot N also gives you E. Remember, these are both in the negative x direction, so in minus signs cancel, these are both in the positive direction. And so I'm going to integrate E times dA twice. And the total charge enclosed is the charge density times A over epsilon naught. And E times A dA's cancel, and I get E sigma over 2 epsilon naught. If you go see the video, that's what I got. Again, we don't have to apply this for a real infinite plane. As long as this thing is very large compared to how far away you are from the plane, you can use this. It's a good approximation to the actual field. And how good of an approximation do you need? Well, it depends. If you're designing something, then you have to take that into consideration, how good of an approximation you want. Typically, if we're off by less than a couple percent, that's a good, for physicists, that's a good approximation for a general system. But if you're designing something where precision is important, then you want to get better at that. Better than another technique. All of these problems that we're doing, we really don't have serious boundary conditions to work with. It allows us to use this form of Gauss's law. If we had serious boundary conditions to deal with, let's say we had we're given the field inside a box, and you have a charge inside the box. What's the field everywhere? We really can't use this. This doesn't work very well. There's another form of this that we can use that makes that problem easier to solve. So the other form of Gauss's law will allow us to do systems involving boundary conditions. When you take a junior level course, senior level course, or a graduate level course, that's what you spend time doing. You're solving the same problem, except that the math is harder. The same physics, just the math is harder. And the only thing different you're considering is the boundary conditions. Okay. Again, when you're doing physics, you want to see the big picture. So when you learn this at the higher level, you look at it. The only thing you consider this new is how to deal with boundary conditions. That's a tough problem. And we spend a lot of time in courses just dealing with that. Okay. Questions? And I am a little bit behind, so I'm going to say this stuff kind of quick. I want to say something about equilibrium in electrostatic fields. If you have a system that's completely governed by forces that depend on 1 over r squared, electrostatic equilibrium is impossible. Now, you might be, if you remember the previous homework assignment, there was a problem in the previous homework assignment where you were asked, is the static equilibrium stable? And the answer was yes to that. And then you might be saying to me, wait a minute, that contradicts what you just said. And the answer is no, it doesn't, because in the problem that you did in the previous homework assignment where the system is stable, 2 of the charges were held in place by non-1 over r squared type forces, non-Coulombic forces. Okay. What I'm referring to is a system that's completely governed by 1 over r squared type forces, Coulombic forces. If you have a location, you place an object at a location where the force on it is 0, it's equilibrium. Because F is QE, the electric field at that point has to be 0. If you take the object and displace it to the right or to the left, if this equilibrium is stable, then there has to be a restoring force that makes it want to go towards the equilibrium position. But you can show that if that's the case, then there has to be a charge at the place that you just removed the charge from, which doesn't make sense. And you can do that using Gauss's law. So stable equilibrium in electrostatic field, pure electrostatic fields, is impossible. And there's a much more deeper way to express this using Calc 3, but I can do that. Okay. So I want to say some things about conductors and equilibrium. Because you do have some homework problems involving conductors and equilibrium. Conductors behave differently from insulators. Why? Because in a conductor, the electrons are free to move. In an insulator, they're not. And so we need to make an important distinction between the two systems. And when a problem is posed, you need to know whether you're dealing with an insulator or a conductor. That has to be stated in the problem. Because otherwise the results will be different. So if I give you a problem that's in a test, and I don't tell you whether it's an insulator or a conductor, you got to ask me, what is it? Because otherwise, the answer to the problem will be different. In fact, in one case, the problem might be impossible for you to solve, given your level of math. Let me tell you some properties of conductors and equilibrium, then I'll talk about it. Number 1, if you have a conductor in equilibrium, means that the forces on all the charges in them is 0. Then the electric field inside it has to be 0. I'll elaborate on that. Any charge any net excess charge that is on a conductor must reside on the surface, not inside the conductor. The field on the surface of a conductor is always perpendicular to it, and we can show that it's equal to sigma, the charge density, the local charge density, over epsilon naught. and that the field, the sigma and the field are greatest at the sharpest points of the surface. So, when you have a conductor that's placed in an external field, okay, let me draw a picture. NEO conductor, solid piece of metal. And here's a conductor. And I place it in a field. The charge will redistribute itself, and notice that it redistribute itself so that the total field inside it is zero. It'll actually create a field in the opposite direction within it, equal and opposite to this, to cancel this out. Why must it do that? Well, if you have a bunch of charges, well, first of all, if you have a system in equilibrium, then the sum of all the forces acting on the charges has to be zero. That's what equilibrium means. The sum of the forces have to be equal to zero. If the sum of the forces equals zero, guess what must E be? Zero. If there's a field inside here, this is not zero, that's not zero. Okay, so by that, if we define the system to be in equilibrium, and this system will be because the electrons can't go anywhere else but inside the conductor, they can't go outside the conductor. Unless the field is so large that the atmosphere breaks down, it's called a coronal discharge. I'll show you a video of a coronal discharge, it's kind of cool. I'll show you one later this semester. But if you make the field real high enough so that everything breaks down, then you can get weird things to happen. But assuming normal conditions, you put an electric field here, the inside will create its own field in the opposite direction and cancel it out. Because otherwise, because it's in equilibrium, F has to be zero. If F is zero, E has to be zero. So the field inside the conductor has to be zero. And actually, the conductor itself will do it, it is an estimate, in a time of about 10 to the minus 16 seconds. So if I take this and place it in an electrostatic field, the charge will redistribute itself in 10 to the minus 16 seconds, so there's no field in it. That's how fast it does. And I don't think anyone's measured that. We do have the ability to measure times that small. But how to make this measurement, that would be cool. So, having said that, since the electric field inside the conductor has to be zero, if I place any extra charge on the conductor, it has to stay on the surface. If I put a charge on the conductor, even though the electrons are free to move anywhere in the conductor can only reside on the surface. Why is that? Well, again, draw an arbitrary conductor. Whether or not it's an electric field is in there. So here's an arbitrary conductor. And I put a charge on the conductor. Remember, E has to be zero inside, which means that if I use Gauss's law, let's say I draw an imaginary surface, this red thing is the imaginary surface, that matches the shape of what I drew. If E is zero, and this system is isolated, then if this is 0, this has to be 0. And this has to be 0 all the way up to the surface of the conductor. I can make this bigger and bigger and bigger all the way to the surface of the conductor. E has to be 0 inside it. So where does the excess charge go? It has to be on the outer surface. The only place it can go is on the outer surface of the conductor. Because otherwise, the system will not be in equilibrium. Okay. Now, what about the electric field? Let's say this thing is charged. Let me redraw my picture. And I'll redraw my conductor. Okay. And there's positive charge. Let's pretend there's positive charge on the surface. I claim that the electric field at the surface must be perpendicular to the surface. That's my claim. You might say, well, why? Is that a top view of the conductor? It can be any view. This is just the surface. It could be in any direction. Because this is just some weird shaped conductor. I mean, if you want, I can do I can do this. Either way. And then the slide comes out of the board, so you can say that this would be a side view of it or whatever. This would be a cross-sectional view in this case. But it doesn't really matter in regards to my description, what I'm going to say now, whether it's a top view. What I want to say is that the field always has to be perpendicular to the surface. That must be true. So here, you're going to see field lines doing all kind of weird stuff here. But right at the surface, this angle is 90 degrees. And you might see, once it leaves the surface, you're going to see the field lines bending because they can't cross. Okay. The field lines can't cross, you're going to see all kind of weird stuff happening. Okay? All right, so why am I claiming that? Well, suppose I have a field that points at an angle. What would that mean? Well, it has a component along the surface and a component perpendicular to the surface. If you have a charge on the surface of a conductor and there's a field along the surface of the conductor, guess what the charge is going to do? It's going to want to move along the surface because F is Q times E. Because it has a path to go along, right? You can give it this, it has a path all the way around this thing. So you cannot have a component along the direction of the surface. That's called a tangential component. You can only have a perpendicular component. Okay. That's number one. And we can evaluate the electric field locally on the surface by using Gauss's law. So I'm going to choose my pillbox again. Remember, the field inside is 0. Oops. So I'm going to draw my little pillbox, let's say right here. So I have a field pointing perpendicularly outward here, but I have no field here. I apply Gauss's law to calculate the electric field at the surface. So my pillbox, my little pillbox on my cylindrical surface, remember, if the electric field is going this way, the field line is only going to penetrate through the circular part, like the disc-like shape of the cylinder. And so on the top surface, I'm going to get the electric field times A. But on the bottom surface, I'm going to have 0 times A. And that's going to be equal to the total charge enclosed inside this area. And we get E times A. So E is sigma or epsilon naught. So that's going to be the field locally, whatever sigma is at that location. Because you have something that's a weird shape, sigma is going to vary all along the surface. Okay. It's very important for you to understand that insulators and conductors are different. You know, here's an example of 2 charged spheres. And you're asked to find the force between the 2 spheres. Why is my second term 0? Because the field inside 0. Because I'm going to have 0 times A, because the conductor has no field inside it. Is that okay? Okay. So let's say I have 2 spheres, and they're insulators. Finding the force between them is actually very easy because you can treat them like point particles and use Coulomb's law. But if they're conductors, this is a horrendous problem. You still have people writing papers on this problem. Okay. And why is it horrendous? Because the electrons are free to move. So you're going to get some bizarre charge distribution on both objects. And applying Coulomb's law is not an easy thing. You actually will not get an analytic solution for this problem. It's a very difficult problem if it's a conductor. That shows you how it changes when you go from insulator to conductor. This is a horrible problem if it's a conductor. Okay. So we have to be careful in specifying how we deal with a conductor or insulator. So let me show you a picture of the electric fields inside a conductor. Let me blow this up here. So I have 2 conductors. One's basically circular. It's hollow conductor. And then you also have, that's probably a plate. It's a top view. Okay. Now, the field lines. Remember, these are threads. These are the same type of system I showed you before. What you see are threads. The threads are forming the field lines. Look at inside the conductor. No field. There's no field inside the conductor. Okay. These conductors have equal but opposite charge. Now, if you look really close to the surface of both conductors, you will see that the field lines, the threads, actually are perpendicular to the conductors themselves. And you start seeing the edge effects. Look at the edge effect. If you actually remove this, you would actually see the edge effects. Too bad I don't have one where you can actually see the edge effects. This is a nice demonstration of showing you what happens in conductors. Now, one of the things I also want to say is that if you have conductors that have a sharp surface, the charge density is highest at places where you have the least radius of curvature. Where you have sharp edges. Where you have sharp edges, the charges can't move around. And so they get stuck there. You get a higher charge density. Higher charge density means higher electric field. That's why things like lightning rods work the way they do. I will do a somewhat more rigorous example in the next chapter of this idea. Again, there's a hard problem to solve in this class. Okay, to do it rigorously. But here I'm giving you a hand-wavy argument as to why the fields are sharpest at, the fields are greatest at the sharpest point of an object. Here's an example showing you this. Here's the conductor, the pointy end of the conductor. Look at how bunched the field lines are at the pointy end as opposed to the other side. So I'm going to have, I haven't been able to do the videotape demonstrations because I haven't been able to go on campus. They actually closed the campus yesterday. So I'm going to try tomorrow to videotape an example that combines all these ideas. And it has to do with shielding. It is this idea, these ideas here, that make shielding possible. Imagine you have a big cage with a special name called a Faraday cage, a big metal cage. And you're standing on an insulator. And a lightning bolt strikes that cage. Question is, are you going to feel anything? Like if you ground it's even better. But are you going to feel anything? You won't feel anything. Because you have a conductor. You know the electric field inside a conductor has to be zero. Okay? You know the electric field inside the conductor has to be zero. And so you won't feel anything. And so this is called shielding, electrostatic shielding. Actually, electric shielding. And this is called a Faraday cage. And so what we're going to try to do tomorrow is make a video of this, and we'll probably, just in the name of time, I think I'll probably do is email it to you if I can. If not, then I'll put it to you in the next class meeting. Okay. I would do it in my room here, but like I think I said this morning, I can't really bring Van de Graaff close to my computer because I'm at below something on the computer, or a speaker card or video. Okay, I don't want to do that. And I couldn't teach. Okay, so I want to do one last example, and then we'll be done. I think we're towards the end already. I don't have much time, but I'm going to go through this example. I want to calculate the electric field everywhere for this system. So let me redraw the system on the board. So as you're looking at the problem, I'm going to erase the board and draw the picture, and then I'll switch views. Let's give it a second. And the problem you're seeing is very similar to a homework problem. Again, I think it was like number 9. Okay. So let me switch views here. So I've drawn it here. They're spheres. I know they're not perfect spheres, okay, but they're spheres. The inner one has a charge. Initially has a charge plus 3Q. The other one initially has a charge negative Q. Don't worry about how we set this up. Let's pretend we set it up and got this going. So now, once we set this up, what can we say about the electric fields everywhere? The inner material is an insulator, the outer material is a conductor. So I'm going to do the easy stuff first, and then I'm going to do the hard stuff last, if you don't mind. I didn't draw the radii. Let me draw the radii. So the little sphere, radius A, the inner radius of the outer sphere is B, and then the outer radius of the outer sphere is C. One of the easy things for me to do is finding the field between A and B. I'm sorry. Yes, between A and B. I want to find the field between A and B. Look, if I'm in this region, the sphere acts like a point charge. I can write down the field. Done. So this equation is defined in this range. Now, what if we go between points B and C? What if we're inside the conductor? What if we're inside the conductor? What's the field inside the conductor? 0. That was easy. Let's talk about that briefly. Suppose I apply Gauss's law. And I draw a cylinder, a sphere that's inside the shell. I'm saying the field is 0. Oops, sorry. I'm saying that's 0. And you might object to me saying that because inside this green sphere is how much charge do you see there? You see a charge plus 3q, don't you? Would you have an objection to me saying that this is true when I have this much charge enclosed? Well, what the heck's happening? Well, this is what's happening. When I set this up, in order for the field to be 0 everywhere inside the conductor, you're going to see an amount of charge equal to minus 3q on the inner surface of the outer conductor. So the inner surface you're going to draw an amount of charge plus 3q on the inner surface. That way, if you integrate all the way around, you have minus 3q plus 3q, that gives you 0. But wait, the total charge on this thing was minus q. If there's minus 3q on the outer surface, there has to be plus 2q. I'm sorry, if there was minus 3q on the inner surface, there has to be plus 2q on the outer surface. So that the total is minus q. So when you put this in, it's going to draw charge from the conductor on the inner surface to cancel out this charge. In other words, cancel out so that the field is inside is 0. Okay. So now we have on the outer surface this much charge. So if I'm at locations outside the sphere, all I see is a charge plus 2q. It's all on the outer surface. And now I'm going to have the electric field. Equal to that. Now the last part is this. Well, now I got to use Gauss's law. I know there's an equation. I know there's an equation in your book. Somebody you guys we already referred to it, but it's always nice to derive things, so I'm going to derive it. So you have a uniformly charged sphere. I'm going to draw a Gaussian surface. Sorry, this is so small. Of radius r. So I'm going to use the same routine as before to use Gauss's law. I'm going to say the integral of E dot dn is this. And that's going to be Q enclosed over epsilon naught. Okay? Just 1 second. Okay. How am I going to get Q enclosed? I want to find how much charge is inside the sphere of radius r. I use the integral of rho dv. I'm going to integrate my charge density. My charge density is uniform. It's just going to be the total charge over the volume. And I'm going to integrate what is that going to give me? I'm integrating r squared. The integral of r squared gives me r cubed. So I'm going to get this. And I'm going to set this, I'm going to put this over here. Okay, so, oops, that's cubed. I'll use r cubed, sorry about that. Okay, so my 4/3 pi cancels. I want to solve for E. Remember that when I'm going to divide both sides by 4 pi here, 1 over 4 pi epsilon naught is K. I'm going to have an a squared in the denominator. And I'm going to be left with an r in the numerator. That's my field inside. Now think about it when I'm on the surface. When I'm on the surface, r equals a, I'm going to get k cubed over a squared, which makes sense. And that equation is this at r equals a. So, in here then, it's linear. So if I were to make a graph of the field, I'm just going to sketch a graph. Inside it varies linearly. Now a bunch of you, probably in the previous course, probably calculated the gravitational field inside the Earth, and you've got some function that's linearly dependent on R. Again, one of the things I said in class, the electric field inside, or the gravitational field inside is going to be 1 power higher than the density. If the density is uniform, then it's R to the 0, like a 1 power higher. Then we hit the surface, so this is B, we got a discontinuity from B to C. Oops, I forgot. I messed up. Sorry. This is A. And from A to B, you get this. And then from B to C, you get 0. And then it jumps up again. Now, how high it jumps up depends on Q and R. Okay. It depends on what A and C are relative to Q. So it's possible that this one could be higher than that one. You're right. Sorry. Oh, right. It's right there. Thank you. Yeah, it should be AQ. Sorry about that. Okay. But that's what the field looks like inside. Questions? Okay. So because I have an appointment, I'm going to run my 3:30 class at 4:30. And if you have questions about problems you'd like to see solved, just email me. I'll take a look. Are we okay? Okay. I guess no answer means it's okay. Okay, you're welcome. So if I don't see you in 210R, oh, you have a question for the graph? Go ahead. From 0 to A. What's your question from 0 to A? Yes, it's linear, right? It doesn't look like a line to you? Or it doesn't look linear enough to you? Yeah, it's based on R. Okay. Yeah, okay. Sorry if it was confusing. Yes, it's going to depend. It's going to depend on this quantity. Anything else? All right, I hope to see some of you in 210. If not, have a good weekend.